Okay, so we are approaching the end of the Fourier series chapter. I've just got one or two lectures left to give on it, so we should be done with it by today. So we're into this. So last week we were doing the odd and even functions and what their Fourier series looks like. Okay, so if you weren't at those lectures, I'd encourage you to view those lecture recordings and so on. So we got one main result to think about, which is this result called Parseval's theorem. But as an introduction to it, we just want to try show you something that's going on with some Fourier series. Okay. And it's going to lead us into a fairly technical matter regarding the convergence of functions. Okay? So this is one of the Fourier series we obtained earlier on, the Fourier series for the function f of x equals x. And it has this Fourier series here. F of x equals x is, of course, an odd function, so it has what's called a sine series. There are no cosine functions in it. Just a collection of sine functions. Okay, so this is the infinite series of these sine functions, and that converges to the function f of x equals x. Now, one thing we might do is to try see here we on either side of this equation here we've got two functions of x. Okay, fairly simple, straightforward function of x here on the left hand side is the quantity x. But there's infinite series of sine functions on the right-hand side. What we're going to do is we're going to try or attempt to differentiate the equation. Okay, so to take the derivative of the left-hand side and equate it to the derivative of the right-hand side. Okay, the two functions are equal. They should their derivatives should be equal. Now, the derivative of the thing on the left is fairly straightforward. It's just the quantity 1. And supposing that we could do so, if we want to differentiate this infinite collection of signs, we'll pretend or we'll assume, we'll act like we can do that term by term. So differentiate the first one, differentiate the second one, differentiate the third one, and so on. Okay? And add all their results together. Okay? So sine x differentiates to cosine, a half sine 2x differentiates to cosine 2x, third sine 3x differentiates to cosine 3x, etc. Okay? Now that all looks okay. That all looks okay until you inspect carefully the resulting equation that you have. Okay, this equation is claiming that 1 equals this combination of cosine functions, or that suggests that this combination of cosine functions is constant. It's always taking the value 1. Well, if it's always taking the value 1, let's try evaluating it at a nice argument, evaluate it at x equals 0. And on the left-hand side, we've still got 1. On the right-hand side, we've got cosine of 0, cosine of 0, cosine of 0, cosine of 0. Cosine of 0 is 1. So on the right-hand side, we have this alternating series of 1, plus 1 and minus 1, plus 1 and minus 1. Which doesn't really make any sense, okay? Because the alternating series of plus 1 and minus 1, plus 1 and minus 1, when you add those up, it's not a convergent series. What you get is a sequence of partial sums that alternate between the value 1 and 0, 1 and 0, 1 and 0, 1 and 0. And there's no kind of conventional way that could be understood when you multiply it by 2 to give you the value 1. So I've said there, which is plainly nonsense. I mean, I wouldn't say it's exactly nonsense, but there is a reasonable way you could kind of fix this. You could argue that maybe the value of an alternating series or an alternating sequence of quantities 1, 0, 1, 0 could maybe give a semi-persuasive argument that should have value a half, the average value of those two alternating values. And 1 is indeed equal to 2 times a half. But that's a bit vague and a hand-waving argument, okay? it doesn't really look correct, okay? So you've got a non-convergent series here equal to a finite number. So what happened? The thing we started from was fine. We had the Fourier series. That was correct. Differentiated it, and we got this contradiction. So what went wrong there was this assumption, this assumption that we were allowed to differentiate an infinite series, which is what we would have had at the very top, taking the derivative of the left equals the derivative of the right. Well, the right is this infinite sum. And we assumed that we were able to differentiate that by adding up all the individual derivatives. Okay? So it's this thing, it's this process here that the question mark is around. Okay? This example shows that you're not always allowed to do this. Okay? You're not always allowed to do this. Now, and this is a delicate matter, because if these were finite sums, these sums just had some finite number of terms in them, then you, of course, are allowed to differentiate a finite sum of functions by differentiating in each individual one and adding up the results. That's just the plain linearity property of the derivative. Okay? Something we proved in maths fundamentals. That differentiation process is linear. Okay? So for any finite sum, this equation, there's absolutely no problem with that equation. Okay? The problem comes is when we assume that we can extend it to infinite sums. It doesn't automatically go through. For certain classes of infinite sums of functions, this will be fine. Okay? But for others, it won't. Okay? And the issue comes down to the convergence properties of the infinite sum of functions. Okay? So there is more than one way that a sequence of functions, here thinking about the sequence of partial sums, there's more than one way that a sequence of functions can converge to its limit function. Okay? So the terms are, which I'd like to tell you about and help you understand, is a uniform convergence and pointwise convergence. Okay? So on the pen and paper now, I'd just like to tell you about pointwise convergence and uniform convergence, explain to you the difference between them. And then you'll be able to understand these statements of these theorems at 3.6 and 3.7. Okay? So this is convergence of sequences of functions. So just to make it clear, Fourier series provide examples of sequences of functions. Now you're well used to thinking about sequences of numbers. It's what we started off doing in maths fundamentals, having fun with sequences of numbers all those years ago, 1 year ago. But you can have sequences of functions. So a sequence of functions would be a sequence fm, that converge to a limit function f as m tends to infinity. And of course, the way that those are presented to us in Fourier series is where the fm of x is the partial sum. So sum n equals 1 to m of an cosine of nx plus the sum n equals 1 to m bn sine nx. So that's the Fourier series. This is the expression for the Fourier series of the function, but with the upper limit of m on the finite sums, not infinity. So F1 is just, say, the constant term and the first cosine and sine term, if they're there at all. F2 would be the cosine, the constant, the first two cosines, the first two sines, etc. So the higher and higher m is, the more and more terms are brought into these sums. The longer the Fourier series is, written out as a sum, And the better and better that that partial Fourier series sum approximates the limiting function. Okay? Now, if we recall the definition, I'll remind you last year. Recall the definition for convergence of convergence of a sequence of numbers. Say we had a sequence of numbers, say xn, converging to some limit number x as n tends to infinity. Right? How did we define that? We defined that using our epsilon n definition. For every epsilon bigger than 0, it was possible to find a point capital M such that for all values of little m bigger than or equal to capital M, we had the absolute value of xm minus x being less than epsilon. Okay, you'll remember that definition. X was the limiting value. Epsilon is any radius of an interval around the limiting value. And the convergence definition said no matter what size of epsilon bigger than 0 you take, but for all values of epsilon bigger than 0, so for all intervals centered on the proposed limit, there is some point or is some occasion, capital M, such that for every point or time after that, the sequence element, this absolute value is less than epsilon. That means the sequence element is living inside this interval. This condition here means that xm is living somewhere in this interval. Yeah, the distance from xm to x being less than epsilon. Xm minus x, this absolute value, which is the physical distance from xm to x, it's going to be less than epsilon. So that means xm must be somewhere in here. If it's outside here, the distance to x is bigger than epsilon. Okay, that's the definition of convergence for sequences of functions. But convergence of functions can happen in at least 2 different ways. And the 2 types we're going to look at the definitions just to understand the differences in what they're saying is pointwise convergence and uniform convergence. The pointwise convergence, remember now, we're in this setting where we've got a sequence, not of numbers, but a sequence of functions that is converging to a limiting function. Just like in the demos, the animations or the interactive demo I showed you, where when you increase the index, you got more and more terms brought into the Fourier series. You got your partial Fourier series function getting closer and closer to the limiting function. It was always oscillating around it whenever you cut off the Fourier series at some finite point, but it was getting closer and closer. The oscillations were getting tighter and tighter around the limiting function. The pointwise convergence says at every point in the domain, at every point x in the domain, we get a convergent sequence of values fmx converging to f of x as m goes to infinity. a convergent sequence of values in the normal convergence of number sequences way. Convergence of number sequences way. That we just defined up above. Okay. So this is called pointwise convergence, where you pick out a particular point x in the domain of the function. And then if you're only looking at that point x, you ignore the rest of the domain function, you're just looking at that point x, then the sequence of function values given to you by f1 of x, f2 of x, f3 of x, f4 of x, that this sequence of function values is getting closer and closer to the limiting value f of x. Okay? In the normal convergence of number sequences way, this definition for convergence of sequences that we just described. So that's what's called pointwise convergence. You focus on a single point and you ignore the rest of the world, and then at that single point, you get a sequence of numbers, it's the values of each of the sequence functions, f1x, f2x, f3x, evaluated at x, it gives you a sequence of numbers that converges to the final number f of x. So the crucial point about this is there's no requirement about the overall rate of convergence, okay? Just as long as you've got a convergent sequence of values at each point x, then we can say that the sequence of functions converges to f pointwise. At every point, it converges. So that would be, i.e., that would be saying for all x in the domain, I'll just leave that as for all x, and then it would run much like the definition we've just given. For all x, for all epsilon bigger than 0, there exists an m such that m bigger than or equal to capital M implies that the absolute value of m of x minus f of x is strictly less than epsilon. Okay, so that's pointwise convergence. And that is in a sense the easiest kind of convergence to achieve. It asks the least of the sequence of functions. It doesn't make any claims or requirements about the different rates of convergence that there might be at the different points x. It could be at some points x, the function is converging really fast. The functions fm are converging very fast to that. Could be at other points x, the convergence is very slow. So you could have different rates of convergence at different points of x. And we can tell that it allows different rates of convergence just because it makes no it makes no claim or requirement about it. So this allows different rates of convergence at different points x. So it's like saying, let's all go to Liverpool. And we will all go to Liverpool if at some point every individual one of you makes it to Liverpool. Okay? But maybe I get there in a couple of hours. Maybe some of you get the bus. Some of you walk. We might all arrive at Liverpool at different points in time. But as long as eventually each one of you gets to Liverpool, each one of you converges to Liverpool, then we might have said that student-wise or person-wise, individually, we've all converged to Liverpool. Okay? Well, there's nothing wrong with Liverpool. Closer to Dublin, so it's automatic. But a stronger way in which we might all go to Liverpool is if we all go there together. We all get a coach together. We get in the same train. Okay? So this leads us to a stronger form of convergence. So stronger is this word we often use about mathematical results and definitions. Stronger means there's more to the definition. It's a tougher criteria to satisfy. Knowing that something is this second type of convergence, it tells you more about the function. So this is called uniform convergence. Now this is where we change this statement here. So the pointwise convergence allows different rates of convergence at different points x. Now we're going to get rid of that. We're going to insist that there's one overall uniform rate of convergence that's observed. Okay? We all go to Liverpool at the same speed, all of us together, because we're all in the same domain. Okay? So this is called uniform convergence. So this is uniform convergence where the convergence happens at the same rate. Well, it's not quite technically true, but what it means is that there's some bound. There's some bound to the different rates of convergence that happen. That happens. So it's possible to declare a single rate of convergence that all the individuals, students here, or points x in the domain, so it's possible to declare a single rate of convergence that's honored or respected by all the cases. Okay? So where the convergence happens at the same rate, or more correctly, a bounded rate. Some points might still go there quite fast, but there's nobody left behind. It's taken crazy amounts of time to get here. More correctly, a bounded rate. Where the convergence happens at the same rate at all points in the domain. At all points x in the domain. Now, this is really brought into sharp focus when you look at the symbolic form of the definition. Symbolic form says for every epsilon greater than 0, there exists an there exists a capital M, such that if little m is, or let's say such that for all x in the domain, little m being greater than or equal to capital M implies absolute value of f of m of x minus f of x is less than epsilon. At first glance, it looks like I've just written down exactly the same thing that I wrote down before. Right, it's the same inequality at the end. You've got this implication. If you're past the point m, then your f of x, your fmx value is close to the value f of x. Right? But what's different, of course, is the location of the quantifier over x. Okay. Pointwise convergence, the for all x is at the front. So it says just for every value of x, it's possible to do the rest of the statement. But the uniform convergence says it's possible to arrange this rate of convergence such that at every point x, the inequalities are satisfied. Okay? So the place where you mention the x is moved inside the epsilon and the capital M quantifiers. So the difference between the two is all to do with the locations of where x is quantified. So the uniform convergence says if somebody specifies a closeness to the limit, for every epsilon bigger than 0, somebody declares a closeness to the limit, it's possible to find a point in the sequence of functions, there exists a capital M, such that at every point in the domain, so after the epsilon has been set, after the capital M point in the sequence of functions has been declared, it's then true that at every point x in the domain, the value, if m has gone past this point capital M, then the values f of x, or the values fmx, are within a distance epsilon of the limiting value f of x. And that this is true now for every point x in the domain. So there's for a given epsilon, there's a single point, capital M, that works for all x, in the uniform case. Whereas in the pointwise case, it's possible that for a given epsilon, that there be different values, capital M, at different points x, okay? So the epsilon closeness might be achieved very early on for certain values of x, and very late, much further on, for other values of x, okay? But the uniform convergence says for a given value of epsilon, the epsilon closeness is achieved at all points x after a certain point, okay? So there's some bounded rate. Some points x might take a little bit slower than other points x, but there's a bound to how slow that convergence can be happening. If you set the speed of convergence at that lowest possible bound, you'll see all the points x converge, or all the values of fmx converge to f of x at that rate or better. Okay. Now, uniform convergence allows us to say things like that if we want to differentiate the limit function, we can do that by differentiating the sequence functions and taking the limit as n goes to infinity. Okay. These things are explored very carefully in mathematical analysis and real analysis. But one of the crucial consequences of uniform convergence is this, that if you want to differentiate the limiting function f, you can do it by examining the limit of the derivatives of the sequence functions. Okay? But that doesn't necessarily work when the convergence is only pointwise. And this implies that if the sum of n equals 1 to infinity of f of n converges uniformly, to f, so f is equal to this sum n equals 1 to infinity of f of n, then if you want to differentiate f with respect to x, in other words, you want to differentiate the infinite sum with respect to x, you can do that. So this final step is what uniform convergence allows you to do. You can do that by differentiating each of the sequence functions and taking the sum, series functions, and taking the sum of those derivatives. So it gives you the kind of infinite linearity, or the linearity over infinite sums. So you cannot automatically assume, just because you've got linearity over finite sums, that you then have linearity over infinite sums. You need a good, strong form of convergence, such as uniform convergence. Okay. So let's go back to the notes now and look at how these concepts are used. Okay. Pointwise convergence says when you focus to the exclusion of everything else at a single point x, then you've got a convergence sequence of values, fmx converging to f of x. Very weak. It just as long as that's true at every point x. Uniform convergence says effectively that there's a single rate of convergence, and that at every point x in the domain, the convergence is happening at that speed or better. So let's switch back to the PC now. And actually, I'll show you. I should go back to my the Fourier series of the square wave. Let's go back to this one. This is one of the first examples I showed you to illustrate Fourier series. Now, this animation is showing you the Fourier series in blue for the square wave function. So a short bit of the square wave function is shown in red here, stretching from minus pi to pi. It's the function that takes the value 0, and then it jumps to 1, and then it's going to go back to 0, then it's going to jump to 1, go back to 0, jump to 1. Okay, so it's basic signal, produces a tone. If you pass it through a speaker fast enough, it will produce a sound you can hear. So this is the square wave function. In blue is given the order 10 Fourier series for it. Okay, where you're summing the terms of the Fourier series just up to order 10. You got this wavy blue function which is doing the best it can to stay close to the function. Okay, now this is converging to the function, right? Because as you increase the order, the oscillations of the blue around the red are much tighter, right? But you start to see how this convergence is not uniform here, okay? Because if you're in the middle, if you're far away from the point of discontinuity, you're around pi over 2, the convergence is already quite good because the blue is more or less being obscured by the by the thickish red line. Okay? So the convergence is happening quite fast, close to pi over 2. But when you're close to this point of discontinuity, the convergence isn't so great. You see why we see, relatively speaking, relative to what's going on here, relatively speaking, we see quite large variation from the limiting value here. Okay? These points very close to 0, these are still quite far away from where they should be. But the thing is that this phenomenon never goes away. You go to order 63, you've basically got good convergence everywhere except quite close to the point of discontinuity. Should regenerate. Here comes, still thinking. This is what we referred to earlier as the Gibbs phenomenon. But around these points of discontinuity, we can always have these fluctuations. So, yeah. So, like, you know, we may as well say the convergence has been achieved. The error is extremely, extremely small over most of the domain. Okay. But there's still this troublesome part of the domain where the convergence is bad. Okay. Now this wobble, this Gibbs phenomenon here, it's being pushed further and further. It's being squeezed further and further, or closer and closer to the point of discontinuity. So the good convergence, which is more or less perfect here, is the good convergence area is widening and widening. But it's just kind of pushing this kind of weird oscillation effect closer and closer to the point of discontinuity. But it will always be there. Right? So this is an example of convergence that is pointwise. So at every point, if I just select one value of x, like this value of x here, I keep increasing the order, I'll eventually see the blue curve being, you know, never deviating, effectively not deviating from the limiting function. Okay? Only tiny microscopic amounts, right? If I select any individual point x. But if I stand back and say, well, across the whole domain, I want to see agreement within, you know, agreement within a distance of a millionth between the Fourier series and the limiting function. There's never any point that that convergence is achieved across the whole domain. Because there will always be, very close to the point of discontinuity, there will always be these weird, large oscillations. This is the Gibbs phenomenon. Okay? So we can't find, I'm just trying to persuade you here that we can't find for this Fourier series, given a degree of closeness required for the blue function around the red function, whatever degree of closeness is required, it's impossible to find a single point where that closeness is achieved across the whole of the domain. That's the key phrase, across the whole of the domain. If we pre-select any individual point in the domain, yes, there will be a point in the Fourier series of a very high value of m, and the Fourier series will achieve the closeness at that value of x, right? But there will still be other points x that it won't have achieved it yet. Okay. So we have this large Gibbs phenomena oscillation close to the point of discontinuity. Now, so this convergence is not uniform, not uniform. The reason, why it is not uniform, it's caused by this discontinuity problem. Okay? So the discontinuous jumps in the underlying function f, the red function there, those are what make it impossible for the Fourier series to converge uniformly across its whole domain. Okay? So if we look at the rest of the statements here, we can appreciate at least what's going on with these results. Okay, now we're not going to. I'll give you a kind of a proof for Parseval's theorem. But this theorem 3.6. So this is the key technical one. This gives us conditions which will guarantee that the Fourier series converges uniformly to the limiting function. Okay, we've just seen an example with the square wave function where I tried to at least illustrate to you that the convergence is not uniform. You've always got these large oscillations that are always there. But these conditions here stated in theorem 3.6 will guarantee that the convergence is uniform. So it says the Fourier series for f converges uniformly if, so the first part we need to know that f is continuous on the interval. Okay, so that would immediately rule out that example I just showed. That example is not continuous at 0. It makes a jump of 1 at the point 0. So your function f has to be continuous. The function df dx, the first derivative of f has to be piecewise continuous. Now that would allow functions like, so that would allow some non-smooth functions like that have sharp points in them. But this was the function f. It's certainly continuous. It doesn't make any discontinuous jumps, but its derivative does make a discontinuous jump. That was f. This was the function f. The derivative of f would look something like, well, the derivative is, it's increasing here, so it's some positive value here. As soon as you pass this point, it instantaneously becomes decreasing. So that would be a graph of df dx. Okay, the derivative of f. So we're allowed. So these conditions allow points of discontinuity in the derivative. Okay, but the derivative must be piecewise continuous. This is made of continuous pieces. And also, because these Fourier series, fundamentally, they just, well, the way they're presented here, they just look at the interval minus pi to pi. We would have to have no discontinuities at the edges. So the function on minus pi to pi would have to agree at the boundary. So which this function kind of looks like it does. It looks like it reaches the same height at minus pi as it does at pi. Okay. So as long as that was true, as long as that is true, that's the last condition needed. Okay, that effectively means that the function is continuous everywhere, and it agrees with itself on the boundary of pi and minus. Okay, so theorem 3.6 says as long as these conditions are satisfied, then the convergence is uniform. And 3.7, our kind of final theorem in this unit, is a nice fact about uniformly convergent Fourier series. Okay, so if we know that the Fourier series is uniformly convergent, Parseval's theorem tells us, well, it gives us this result here, which looks kind of a bit odd, but it's telling us something about the integral of the square of the function. And it's relating that to, so you see the sines and the cosines have gone now. We've integrated the function over all the values of x. We've integrated the square of the function f. But there's no x's left around because they've been integrated out. And here we kind of more or less have the sum of squares of all the coefficients. Okay. So Parseval's theorem gives us something equivalent to something you're slightly more familiar with in lower dimensions. So thinking about Parseval's theorem. Yeah, think of a vector x in V3R, three-dimensional vector space. Your vector x, we can write as x1, if we're using the standard basis, or any basis really. Okay, so you can express the vector x as a linear combination of the basis vectors. Basis vectors, yeah. And then you have this idea that the norm, the square of the norm of the vector, which one way of thinking about it, or at least one example of that kind of a thing, is the norm arising out of the dot product, scalar product, standard scalar product of two vectors. Well, that quantity is the sum of squares of the components. Okay, you take the inner product, the dot product of the vector x with itself. Because the basis is an orthonormal basis, EI is the standard orthonormal basis. Orthonormal means, well, the ortho bit, the orthogonal bit, means that each of the basis vectors is orthogonal, perpendicular to all the other ones. The normal bit means each of them individually is a unit vector. And the consequence of that is that the square of the norm of the vector, the inner product of the vector with itself, is the sum of squares of the coefficients. Okay? So Parseval's theorem says kind of the same thing. So instead of the inner product squared of the vector, we're talking about the integral of the square of the function, f of x squared. Let's put the square right here, f of x squared. And Parseval's theorem more or less says that the integral of the square of the function is the sum of the squares of the Fourier coefficients. Now, there's a little bit of a twist and rescaling going on, that we've got this quantity 1 over 2 pi at the front on the left-hand side. And, well, because of the choices made when we were setting up Fourier series originally, and how we represented the constant term of the parameter A0, we'll have a quarter of A0 squared, and then basically a half of the sum of the squares of all the other components. So all the AN squared plus all the BN squared. So you should look upon these two things as being, well, in some sense, the same, or equivalent. Or, you know, this kind of thing is an example of the same phenomenon that's happening here with your regular vectors, your regular scalar product, something you've been familiar with since last year at least. Okay. But we need this technical condition that the Fourier series for f, which is where these coefficients come from, that Fourier series is converging uniformly to the limiting function f. Now, in this evening's lecture, I'll show you a kind of a proof of Parseval's theorem, or a strong argument for it that uses that idea that uniform convergence allows you to differentiate or integrate term by term. And we'll look at, there's a final example to do, example 3.9, illustrating the use of it. And then I might have a few more remarks to make about the Fourier transform and so on before we finish, okay? So from next week on, I'll start to do revision activities, such as some past exam questions and so on. Okay, so I'll see you all later on.